Alright, g'day, welcome back for part 2 of topic 1 of week 10. We're going to be continuing our discussion of heat and calorimetry. We talked in the first video about applying heat to something and seeing a temperature change result. And we talked about how the amount of temperature change that results depends on the material the substance is made of. Because each different type of material will put a different proportion of the heat energy they get into translational kinetic energy, and that's the bit that we measure when we measure temperature. So if they put a different amount in, then for the same total heat energy going in, the temperature is going to change by a different amount. So that was specific heat capacity. Now we're going to continue on with our discussion of heat and calorimetry, but we're going to be looking at phase changes. So we'll go straight to phase triangle. There we go. So we're looking at different phases now. You should all be familiar with this concept. We've got a solid, bottom left, melts into a liquid, liquid freezes back into a solid, liquid vaporizes into a gas, condenses back into a liquid, and a solid that goes straight to a gas is sublimation, and it deposits or deposition back into a solid. So you should all be familiar with that. We're not going to go into any more detail on that. Other than to point out that evaporation is vaporization that just occurs when it's not the whole liquid all at once, right? Heat and phase changes. So sometimes when we heat a substance, it doesn't increase the temperature. Sometimes the heat energy that we give a substance goes instead into breaking the bonds between the molecules that form either the solid or the liquid. So if you're breaking the bonds that form a solid, then the molecules are now free to move around. They're not stuck in place. So by giving it that energy, you're turning it from a solid into a liquid. Similarly, once it's a liquid and you get it to its boiling point, if you give it enough energy to overcome the attraction to all the other liquid molecules, then it will fly off away from the liquid and become a gas particle. And so that's the evaporation process. Both of those processes require a lot of energy. Right? It takes quite a lot of energy to overcome those bonds. But the point is, once you get to that boiling point or that melting point, depending on which phase you're looking at, once you get there, the energy goes into that process of breaking those bonds and changing that phase, and it stops going into translational kinetic energy. So once we get to the phase change, we stop getting any temperature change until the phase change is complete. All right? As an example, let's take some water, frozen water, so it's ice. It's below 0 degrees Celsius. We apply heat, the temperature increases. Right? So at the moment, it's not about to melt. It's still really cold. It's somewhere below 0 degrees Celsius. We give it some heat energy. It's going to put some portion of that heat energy, based on its specific heat capacity when it's ice, into translational kinetic energy. And that means that the particles will all be So when we talk about vibration and translational kinetic energy in a solid is like a vibration, but it's a bit different from what we're talking about. I'm actually just going to clarify this a little with a diagram, with a sketch rather. So when we talked about internal energy vibration, we said here's a water molecule, and the internal energy vibration we're talking about was that these can go back and forth like little springs. So the hydrogen molecules can bounce back and forth with the oxygen one. And so the whole particle is vibrating within itself, right? In that case, the particle is a molecule and the vibration is occurring within that molecule. When we're talking about a solid, we're saying here's some objects all bonded to each other. All right, these are all bonded to each other. I guess I'll draw another one in here. So this is our solid. It's in a grid form. Obviously, it extends beyond it. It's not just these 8 particles. But when we talk about these having kinetic energy, this particle here might move this way a bit, or that way a bit, or in between, or somewhere. But it's got a limit on where it can actually get to. Right? It's got this limit on where it can go, because if it goes too far this way, it gets too close to this particle, and so that will push it back. And if it goes too far this way, it'll get too close to this one, and that'll push it back. So it's got a limit on where it can move. So when we talk about a solid particle having kinetic energy, translational kinetic energy, we're talking about it moving around within that solid, anywhere in here, but it can't go too far because it'll hit its neighbors, it'll get too close to its neighbors and that'll push it back. So in that sense, it sort of looks like it's vibrating. It'll move this way a bit, but then it'll get sent back and then there and there, and so it'll bounce around inside. And so it sort of looks like it's vibrating, but it's actually just moving around randomly within the space that it's allowed. While that's happening, this can still be going on too. So if you think of these as, this is ice, which doesn't have this exact cubic structure, but if you imagine ice as a solid, then each of these molecules is stuck in a certain location, can go a certain distance back and forth, and it'll do this and bounce around on the spot depending on how much energy it has. But within that molecule, we can still have this going on. So we still have vibrational kinetic energy, or kinetic and potential alternating, as we saw with oscillations. We still have that going on within this molecule. Right? And while that is vibrating and within itself, it can still be moving around. We sometimes refer to this as vibration just because the particle is going back and forth, right? It's translational kinetic energy, but it's kinetic energy within a certain location. So hopefully that resolves any confusion that there might have been. I try not to use the term vibration too much when I'm talking about solids gaining kinetic energy. Yeah, but sometimes it is just the best word to describe the motion. You just have to keep in mind it's different from the vibration within the molecule that we're talking about as one of the forms of internal energy. Right. Hopefully that's not too confusing. So our ice is below 0 degrees C. It's vibrating on the spot, vibrating in that sense that we just talked about. And as we give it more energy, it'll vibrate more and more. It'll move around more and more within its little space that it's allowed. As we saw with thermal expansion, that space will actually expand as it gets more energy because it just needs more space. So it'll expand, it'll vibrate a bit more, it's got more energy. But at a certain point, when we get to 0 degrees Celsius, remember that's the average temperature of all the particles in the solid. Once we get to 0 degrees Celsius, then any more energy that you give it will actually overcome those bonds between the neighboring molecules. So now the molecule, the H2O molecule that was moving around inside a certain little space, gets enough energy to overcome those bonds, the ones that are holding it in that certain little space, and now it can move anywhere it wants. Right? It's now free to move around. And so you've got to do that for every single one of the molecules that make up that solid. And while you're giving them all of that energy, the temperature doesn't go above 0 degrees C. The temperature stays there. And that's because if it went above it, that would mean one of the particles was moving a bit faster. But if it's moving faster, then it's going to bounce into one of the ones that's still a solid, still bonded to all its neighbors, and give it the energy, right? And so your one that starts to move a bit faster would lose its energy again and get back to being a 0 degrees Celsius liquid molecule. And then that'll help the next one, the next molecule that it bumped into, it'll help that one get closer to overcoming those bonds and becoming a liquid molecule rather than a solid. So in that sense, all of the particles will stay at 0 degrees Celsius average temperature until they are all liquid. And then once they're all liquid, then it can start to heat up a bit. Now that's not perfect. It's not a perfect exact truth to say that they are all solid, phase change, all liquid. You still do get some little clusters of crystals, some molecules that are still stuck together that stay in the solid form as it moves into a liquid. That's a unique characteristic. It results in a unique characteristic for water in regards to its density, but we will talk about that. I can't remember if I've got a slide on that actually, but I'll add something in later on if I haven't, just talking about the density of water and ice as we get to 0. But that's not the focus of this. The focus of this is just talking about that phase change. So hopefully you can understand why we're giving it the energy, the phase change occurs, the temperature is not changing. Then once the phase change is complete or almost complete, so essentially it's all a liquid now, then it can start to increase in temperature again. As it, so it's just reiterating that, make it really clear, no change in temperature during a phase change. Once it's into a water, so what we're just talking about was this little bit here, the red section of the graph is ice. We're heating it up, we're giving it heat energy, see energy along the x-axis, so we're increasing the energy, the temperature increases up to 0, which is our melting point or freezing point of water. Once we get to 0 degrees, we keep giving it heaps more energy, and it's a mix. It's turning from ice into water. So we've got this mixture of ice and water as our substance, but the temperature never changes. We give it heaps more water, the temperature doesn't change. It just stays at 0 up until the system is all water. Once we get to all water, then the energy that we keep giving it results in temperature change. So it keeps climbing. Once we give it enough energy to get to 100 degrees Celsius, then we stop again. We stop temperature rise again, because all the energy is now going into overcoming the bonds holding it together as a liquid, which means that it will stay at 100 degrees Celsius until it is all turned into steam. Once it is all turned into steam, then the temperature will start to rise again as we keep giving it more energy. And every substance will look like this. You'll have a solid into a liquid, and then liquid into a gas, and the temperature is stationary at the respective melting and boiling points of the substance until it's finished the phase change. You may occasionally see a system where you don't have a liquid phase. So at standard atmospheric pressure, carbon dioxide doesn't have a liquid phase. It goes straight from a solid into a gas. In that case, there would just be one phase change. It would have an increase in temperature as a solid. It would reach its phase change temperature, where it's going to sublimate into a gas, and that would occur at -73, I want to say off the top of my head, Celsius, but you can verify that. It'll get to that temperature. The solid is all at that temperature. The phase change will occur. It'll all turn into a gas, and then once it's all turned into a gas, then the temperature will keep going. Specific heat capacity told us how much heat we need to provide the system to result in that temperature change of 1 Kelvin. The question now, obviously, is how much energy do we require to complete the phase change? As with specific heat capacity, this depends on the material and the phase change it is going through. But unlike specific heat capacity, there is no temperature change to result. So our formula is accordingly a little bit simpler. The different phase changes are melting, which we call heat of fusion, vaporization, which we call the heat of vaporization, and sublimation, which we call the latent heat of sublimation. So we've got these 3 different latent heats. Now these are different for each solid, for each substance, depending on their chemical properties and how they bond and what they do to each other as they form a solid and then a liquid. The latent heat of sublimation, though, is always going to be equal to the heat of fusion and vaporization, because essentially sublimation is just overcoming the bonds that would hold it as a solid and a liquid at the same time. So it's still the same total amount of energy required. The formula, as I said, is simpler. We've only got how much of the thing there is and how much energy it needs per kilogram. That's our whole formula. So the latent heat formula is just Q equals mL, the mass of the substance times the latent heat of whichever phase change you're doing. So we use the one formula, but you have to remember the different phase changes have different latent heats, fusion versus vaporization. Quick example there, because it doesn't need a full 2 slides to show you an example of this. If a substance needs 10 kilojoules of heat per kg to melt, and we've got 2 kgs of it, then we'll need to apply 20 kilojoules of heat, right? Twice as much. 10 kilojoules per kilogram. We've got 2 kilograms, we'll need 20 kilojoules. Now that we've defined latent heat, right, so that was latent heat. Latent heat is the energy required to perform a phase change. Sensible heat is a term that we came up with to apply retrospectively to the bit we've already told you about. We talked about heat that results in a temperature change. We call that sensible heat, because that's what we expect to happen. The sensible just refers to the relationship between the word heat and temperature, that most people have. You expect if you apply heat to an object, you'll get a temperature change. So in this case, it makes sense, sensible heat, for us to have a temperature change when we apply heat. Whereas latent heat, anyway, we don't need to worry about the language of it. Latent heat results in a phase change, sensible heat in a temperature change. Here's a bunch of examples. We've got helium has a latent heat of fusion 5.23 times 10 to the 3, water 3.3 times 10 to the 5. There's a whole bunch of them in there. You can see all the values. I don't need to go through them all. We've got a latent heat of fusion and a latent heat of vaporization for them all. Again, any problems you get, you'll normally be given the constants like this, the latent heats of fusion and vaporization that you'll need. However, you should be familiar with tables like this and being able to get information from them. Also, Googling and finding your own information is perfectly acceptable, but do remember to make sure you're getting reliable resources, not just some random person's blog online. The other thing that's very interesting and hopefully not unexpected is that latent heat is symmetrical. The amount of energy that a substance gives off when it condenses into a solid is the same as the amount of energy that it needs to turn back into a liquid. The energy is purely symmetrical, and that makes sense from a conservation of energy standpoint. If you give it energy, that energy is now stored in those chemical bonds, in the overcoming the chemical bonds. So when the chemical bonds reform, they'll give off that same amount of energy. There's no reason that it would be any different. As promised at the start of the first video, there is a long example to finish this. So long example, iced tea. We've got iced tea. We're going to work through this example as per the name and my warning. It is quite a long example, so do bear with me. If you want to pause it and have a go yourself, you're more than welcome to do that. However, I do not expect you to do that at this stage, given this is the first full worked example of this type of problem, but do hopefully follow along, and then of course try other problems yourself. So we're making a bulk lot of iced tea. We have 500 grams of ice. We have 3 kilograms of tea. The ice is at -10 degrees C and the tea is at 20 degrees C. We want to know the final temperature and phase of the final mixture. So we're putting 500 grams of ice into 3 kilograms of tea. They both start at different temperatures. We want to know what the final temperature and phase will be. So that is the ice cold enough to make that 3 kilograms of tea cool down and freeze it all? Or is the 3 kilograms of tea warm enough that it will melt all the ice and it will heat it up to 0 and melt it and then heat it a bit more? What's going to happen? Where are we going to end up? Are we going to end up partway through a phase change with a mixture of ice and water? Is it going to be all tea? Is it going to be all liquid? Is it going to be all solid? What's going to happen? And we've been given some values. Ice, the specific heat capacity of ice, 2,100 joules per kilogram per Kelvin. Specific heat capacity of water, 4,186 joules per kilogram per Kelvin. Now notice that these are different because solid ice, even though it's the same molecule as liquid water, the solid structure of it changes how much energy ends up into each of those different types of internal energy. So specific heat capacities of the same substance can be different during different phases. And the latent heat of fusion, so this is for melting ice, turning ice into water. It doesn't state that here, but that's the only thing that it could be looking at this problem. The latent heat of fusion is 333 times 10 to the 3 joules per kilogram. So as usual, we'll jump over to our document camera and we'll try and work through this. First thing we want to do is write out everything we know. So we have been told that we have mass of ice is equal to 500 grams. And of course, we want everything in SI units because it's just, it's cleaner for our calculations. That's what we need for our specific heat capacity formula anyway. So we'll just go straight into that. Mass of ice, the temperature of the ice initially, the two ice and initially, is equal to -10 degrees C. The T, so the mass of the T, is equal to 3 kilograms. And the temperature initially of the T is equal to 20 degrees Celsius. And we're mixing that all together, and we want to know what is the final temperature of the whole system. Now, we don't need to specify ice or T for that, because we have the statement that it's coming to equilibrium. We haven't been told that explicitly. They didn't say that in the question. They didn't say this system is going to come to equilibrium, but they asked us what will the final phase and temperature be. And so the only way it can have one final phase and temperature is if the whole system is at equilibrium. Right? It's a requirement for that statement to be answerable. So how do we go about this? Well, what we need to think about is that overall, our system is a bunch of T, Right, here's our tea, and we're taking a bunch of ice and we're putting it into the tea. So here's our tea, here's our ice. What is our system? Well, the system overall is the whole thing, but that doesn't help us because this whole system we're assuming is completely isolated, that it's a closed system. So this is a closed system. And that doesn't tell us anything. All we know is that no energy is coming or going to either of these from any external source, and that doesn't help us solve the problem. So what we're going to have to do is actually look at two different systems within this one main system. So we've got the tea, and that's an open system because it can exchange energy with the ice. And we've got ice as another open system, and that will exchange energy with the tea. So those are two open systems that we're going to consider independently within our closed system that does not gain or lose any energy. The reason we want to recognize that it's a closed system is because it means that any heat that the ice gains must have come from the tea. And any heat that the tea loses must go into the ice. We know it's going to go that way around because the tea is hotter, so the tea is going to be losing energy, the ice is colder, it's going to be gaining energy. So that's what's going to happen, and we've got to think about it this way. So what we have is that the heat lost by the ice is going to be equal to the heat gained by the tea. That's our statement. That's our conservation of energy. The heat lost by the ice is going to be equal to the heat gained by the tea. Other way around, sorry. Heat lost by the tea, heat gained by the ice. But the heat change is the same. Right? That's our conservation of energy statement. So what does that actually allow us to do? Well, what we know is that the ice is going to be warming up from -10 to 0 degrees Celsius, and then it's going to have to melt once it gets there. So while it's doing that, the tea is going to be cooling down, and it can cool down from 20 all the way to 0 before it needs to change phase. Now there's a bit of a problem to solve here, and that is that we don't actually know whether the ice is going to be able to fully change phase. So what I would do personally, the way I would approach this is I would say, what's the most energy the tea could lose before it starts to change phase? All right, so the most energy the tea could lose, so Q of T max, is going to be equal to the specific heat capacity of the tea minus the mass, times the mass of the tea times the change in temperature of the tea. This is maximum for no phase change, right? So that means that this is going from 20 degrees down to 0. So that is a maximum of 20 Kelvin. 20 degrees C, 20 Kelvin, same thing, because we're talking about a step size, a change. So that means that our maximum heat we can lose is going to be that, and we know these values. Right? We know because they told us the specific heat capacity of ice. So we've got C of ice is equal to 2,100 joules per kg per Kelvin. And we've got C of water, which is what we're assuming is the same as T. Another assumption, we haven't been told C of T, we've been told C for water. So we would assume the T behaves exactly like water. I mean, T is just water with some other stuff in it. And so by being given this, we're assuming that other stuff is not having enough of an impact for us to worry about. And that is 4,186 joules per kilogram per Kelvin. So we've got everything we need here. We can figure out this maximum change in heat, maximum heat loss for the tea. And it tells us that it would go a maximum of 3.0 kilograms times 4,186 joules per kilogram per Kelvin times 20 Kelvin. And that would be 251,160 joules. So that's the maximum heat loss of the tea. So if that maximum heat loss of the tea is enough to melt the ice and to bring it up to 0 degrees and to melt it, then that means that our final system will be liquid. If that's not enough energy to bring the ice up to 0 degrees Celsius and melt it, then that means our final system will be a mixture of ice and liquid. Of course, if it's not enough energy to even bring it up to 0 degrees C, then we would expect that it would that the ice would still be completely solid, and the tea would start to freeze. But we can expect that not to happen just by basic consideration of these values. The water gives off needs a lot more energy to cool down, or gives off a lot more energy as it cools down than the ice does to heat up. And we've got 6 times as much water as we do ice. So there's no way that the ice can change by 10 degrees and have the tea change by more than 20 degrees. So that's not going. It's not sensible for that to happen. But it's not necessarily immediately obvious what's going to happen with the fusion, the latent heat of fusion, whether that will be covered completely. So that's our maximum Qt max is 250 kilojoules. So let's figure out how much it would need to heat the ice up to 0 degrees Celsius and then to melt it. So Q for ice to 0 is equal to the C for ice times the mass of the ice times 10 Kelvin. From negative 10 C up to 0 C is 10 Kelvin. So that's our energy required to heat the ice up to 0 degrees Celsius, to its melting point. So that is 2,100 times half a kilo times 10 Kelvin, which is equal to 10,500. You can do this one in your head probably. Half of that is 1,050 times 10, 10,500. 10,500 joules. So of the 251,000 that the tea can give off, it's actually only going to need 10,500 to bring the ice up to its melting point. So now we've got ice at its melting point, and we've still got 240,000 odd joules left. So now we need to see how much energy it will take to melt the ice. So it's now at 0 degrees. We've brought it to 0 degrees Celsius. So what is the heat required? Q for ice to melt. That is going to be equal to latent heat times mass. Remember, that's all our latent heat formula is. There's no change in temperature because it doesn't change while we're changing phase. We've just got how much ice is there, how much energy does it take per kilo. And we said that the latent heat of fusion, L for ice or water, for melting of ice, is 333 times 10 to the 3 joules per kilogram. I should have written that a bit neater, but anyway, we can all see that. 333 times 10 to the 3 joules per kilogram. So now we've got to say what this is based on that, which is 333 times 10 to the 3, and we've only got a half a kilo. So we're only going to need half of that much, because this will melt a whole kilo. So for a half a kilo, it's just going to be half of that, which is, of course, half of 333 is 166.5 times 10 to the 3 joules. So 166.5 kilojoules. That's the heat required to melt ice, melt that half a kilo of ice. And it was 10,000 joules to bring it up to 0 degrees C. And the water can give off a maximum, the tea can give off a maximum of 250,000 joules. And we've just seen that it only takes 177,000 joules to bring the ice up to 0 and to melt it. And so if we bring it all the way up to 170, if we use up 177 joules to melt the ice completely, we still have some energy left over. So that means our system is all going to be liquid by the end. There's enough energy from the tea that it actually doesn't have to give off all of that. It doesn't have to drop temperature all that far. It only has to drop temperature part of the way in order to melt, to bring the ice up to 0 and to melt it. So let's see what temperature the tea would be once it has melted that ice. The total for ice from minus 10 up to melt is equal to both of these together, 166.5 plus 10.5 kilojoules, which is 177 kilojoules. And so that means that at this point, so this isn't the final stage of our system, this is just once the ice has finished melting completely. So once the ice has finished melting completely, the T has lost 177 kilojoules. So the change in temperature for the T at this point is going to be, if we rearrange our formula, which said CMT equals Q, we're going to divide by CM. So C of T, mass of T. Sorry, I did that off camera, but we're just rearranging that formula, Cm delta T equal to Q, and dividing both sides by C and M. So that means that the T must have changed by 177 times 10 to the 3 over the C for T was our C for water, which is 4,186. And the mass of the T was 3 kilograms. So the T has changed temperature by whatever that comes out to be. I will just do that quickly. 177 times 10 to the 3 divided by 4186 times 3. The T has lost 14.09 Kelvin. So that means that the temperature of the T at this point, which is only once the ice has melted, so the ice is melted but still at 0 degrees C, is now going to be 20 minus 14.09, which is 5.991, we'll round, 5.91 degrees C. We have to stick with Celsius now because it's an actual temperature, not a change. That was a change. Kelvin and Celsius are the same. This is an actual temperature. We have to remember that this was Celsius, so this is Celsius. So we're at 5.91 Celsius. Sorry, I keep sliding off the bottom of my camera. Apologies, but I just did the subtraction, 5.91 Celsius. That is the temperature of our T. So now what we've got is a slightly simpler problem. At this point, we have, I'll just write out what we've got now. So we've now got 3 kilograms of T at 5.91 degrees Celsius, and we've got 0.5 degrees of ice water, right? It's a water from the ice at 0 degrees C. And we want to know what will their final temperature be. We've already answered the question about what the phase will be. We know it's all going to be liquid because we've seen that the T has enough energy in it to bring the ice up to 0 and to melt it all and still have some energy left over. So it's all going to be liquid. But we've now got to say we've got these two different liquids mixed together and we want to find out what temperature they're going to be. So what we need to remember is that at this point, we have the mass of the T times the C of T times delta T of the T is equal to the C of the ice, which is now water, times the mass of the ice, even though it's water, it's still the same mass, times delta T of the ice. And what this gets a little bit more confusing, but what we know is that this delta T, this one is equal to 5.91 minus the final temperature. It starts at 5.91, it ends up at the final temperature. That difference is our change in temperature for the T. For the ice, the final temperature is greater than the initial 0, so we end up with 0 degrees Celsius there. Final temperature minus 0 is the change in temperature, going up by TF degrees Celsius. So that tells us we've now got this equation where we know everything except for that final temperature. We know this, we know this, we know this, we know this. And so all we don't know is this. So we just need to rearrange for that. Which is, let's see, we've got C of T is the, C of T and C of W are actually the same now because they're both water. So this is 4,186 and so is this, but we can just cancel them out because they're it's the same number on both sides. So what we get is that the mass of T, which is 3 kilograms, 3 kilograms times 5.91 minus TF is equal to the mass of ice times TF, because the 0 goes away, so 0.5 TF. So what we can do is expand this bracket. So 3 times 5.91. I will just do this on my calculator to make sure I don't make a mistake. 17.73 minus 3F, 3TF is equal to 0.5 TF. So let's bring that over this side. We get 17.73 is equal to 3.5 TF. So we have TF is equal to 17.73 over 3.5, which is 5.066 degrees Celsius. No, actually, we'll leave that in Celsius because that's what we started in. So that means the final temperature is going to be 5.1 degrees Celsius, and it will all be a liquid. And that is the answer to our question. Yeah, that's the answer. So that's quite a long problem, as you can see. Most problems we give you would not be this long, right? This is how long I was working for. We did all of that. We did all of that. And then and all of that as well. Right. So that was the whole problem. Normally, any problems you get will be a little. Oh, actually, you may get a problem like that. It really depends. You should be able to follow that completely. The key, though, is in breaking it up into its parts. Right, thinking about the problem and breaking it up into little parts that you could work out. So what that means in this case was you had to think about what's going on in the system. You've got some liquid, you've got liquid tea, and you've got a solid ice. And you had to think about the fact that if this is warm, then any heat that gives out gives to this. But this is being a different phase, it's going to need to change phase if it's all going to end up as liquid. So you had to think about the fact that it had to go from this system to one where we had tea as a liquid still, but now the ice is at 0 degrees C. So this is minus 10 degrees C. This is 20 degrees C. It's going to go to this where this is now at some other temperature. Right? This is some other temperature. And this is now at 0 degrees C, ready to melt. And it's going to give enough Q for it to melt. So at this point, we were just giving it energy to raise the temperature. So we're giving it some sensible heat. And then we were melting it, so we're giving it some latent heat. And then after that, we're at this point where we've got tea as a liquid and we've got the ice as a smaller liquid because it's now water. And now that it's water, then if this gives it more heat, it's sensible again. It's now going to result in a temperature increase. So that was 0 degrees C water, but now it's going to heat up. And this is again lower again. Right? This is lower again because it's now lost more energy in order to melt the water, melt the ice. So understanding this sort of process, what's going on, is how we would solve that problem. There's no just strict answer for mathematics to say, take this equation and apply it. You have to understand this whole system, what's going on, where the energy is going and how much energy is needed. And then you can use the mathematical formulas to figure out these different temperatures and where everything ends up. And obviously at the end, we end up with one big thing of tea plus ice, which is now all liquid. And as we saw, ends up at 5.1 degrees C. So you need to be able to think about the system. This is one of the things that I always get caught on. A lot of students end up with this viewpoint that physics is just math. And that's not a fault of the students, it's a fault of the education system. We spend our whole secondary education career being told by our teachers that here's your values, find the equation that fits, put it in and do your calculation. That's just math. The physics is actually understanding the system and knowing what's going to happen to it before you do any of those equations. And so that's what I've tried to focus on here. When you've got a problem like this, you can't really just grab an equation. You have to think about what's going on at each step. Right? You have to be able to follow that whole process. So that is the long example. However, there is a more mathematical approach to this problem if you were so inclined. And I will just quickly explain that one. You still have to understand that process, but you may not have to do quite as much mathematical working as we just did. What we know happened is that the temperature that the water had to go up initially was 10 degrees Celsius, and it was ice at that point. So we have the mass of the ice times C of the ice times 10, right, because we have 10 Kelvin. So that's the heat it needed to melt, to go up to zero, to warm up to 0 degrees Celsius, right? So that's to warm the ice to 0 degrees C. I'll put the degrees on the wrong side. 0 degrees C. Then we have ice, so we have to melt it, M ice times the L of fusion, right? So the latent heat of fusion. This is to melt the ice. And then, in addition to those, we have to give it enough energy to raise it to its final temperature. So we have the M of ice times C of water times the change in temperature from 0 up to final, right, which is TF minus 0, which is obviously just TF. We can ignore that. Minus 0 doesn't do anything. So we get TF. So all of that whole thing is our Q into the ice. Just to be same as those, I'll put warm the liquid was ice. Yeah. So it was ice, we melted it, and then we warm it to TF. We have to solve for TF. We know the mass of the ice, C of ice, mass of ice, L fusion, mass of ice, C water. We know all of those terms. This is the only thing we don't know. On the other side, so that was one system. So we had Q going in to that system to do that. But that Q was coming out of the other system. And this other system is just the mass of the T times the C of the T times the change in temperature. Now this was its T initial, which is 20 degrees C, minus that final temperature. Still the same final temperature because we're talking about it coming to equilibrium. So we know that that's how much Q will be given off. The T will cool down from 20 to its final temperature, and that has to give off enough energy, enough heat, to bring our ice from -10 up to 0, then to melt it, and then to warm it from 0 up to whatever the final temperature is. And so then with all of this, you can write one big equation that has everything in it. So it's M ice times C ice times 10 plus M ice times L fusion plus M ice C water now times TF is all equal to MTC of T, which is water again, those are both water, times 20 degrees C minus TF. And now if you rearrange that whole thing for TF, which isn't as difficult as it seems, if you rearrange that whole thing for TF, you can solve for TF with a single calculation rather than having to do the multiple calculations we did earlier. It is still the exact same thought process. We still have to think about what's going on at each phase and how much energy it needs for each step and what the final temperature will be. The more confusing bit here is that what we haven't done is we haven't actually checked that it will give off enough energy for this to undergo warming, melting, and then a bit more warming. What would happen if you were incorrect and if the system ended up partially water, partially ice, is that this would end up negative, TF would end up negative, and that would tell us we've given off more energy than we actually can while it's water, and we'd have to stop and we'd have to adjust our entire equation, because what we'd get is we'd get the ice warming up, starting to melt, but not melting fully, and we'd get the T cooling down and then starting to freeze, but not freezing fully. So you'd get this different result. So this does have a little bit more possibility for not catching some of those errors or some of those scenarios that might be a bit more confusing. Whereas the way we did it first, because we actually calculated that, we said how it's the maximum energy we can lose, and then we checked, well, it takes this much energy to melt the ice, to warm it up to 0, and then this much to melt it, so we know that we're able to melt all the ice. So that little check was actually quite useful. Anyway, that is a fairly long, fairly complicated example, and I do expect that it will be difficult to follow first time through. If you follow that through perfectly, then that's great. If you need to re-watch that, have a few goes at solving it yourself, just working through, making sure you follow it all, That's perfectly fine. Just make sure you do that. Right? Make sure you do get to grips with that whole process, with everything that's going on. That's a good problem because it forces you to think about temperature changes and fusion. But also, as I said, it's not one you can just grab the numbers and plug into a mathematical equation. You can only solve that by understanding the physics concepts. So we'll jump back to the slideshow, but that is the end of the theory content for topic 1. So there is a whole bunch of solutions on there, obviously, as per usual. And that is the end of that. We've got a quick review of all the topics, so take the time to read through all of that. But that is the end of the theory content for topic 1. As I said, this was going to be a slightly bigger one. So these 2 recordings are both quite long. There will be another recording with some questions relating to these topics, so do keep an eye out for that. And then there will be a second and a third topic, which, as I said, will both be a little bit shorter just because we made this week a bit top heavy with this slightly larger topic. But it really does need to be seen as one whole package, right? This whole heat calorimetry all together, covering sensible and latent heats, all needs to be seen together because all the problems that you get will deal with the whole thing altogether. So I'll see you at the next video.